Good afternoon. Welcome to this Institute Colloquium, and we are very pleased to welcome Professor Supriyo Bandyapadhyay to deliver this talk. Professor Bandyapadhyay used to be a very regular visitor to our institute. He was associated in many forms, especially as a Vajra faculty a few years ago, with collaboration with Professor Anjan Borman here. So, before the talk, I request Professor Anjan Borman, our Dean Faculty, to kindly introduce the speaker.
Yeah, good afternoon, everyone. It's a pleasure to introduce Professor Supriyo Bandyapadhyay, who is currently Commonwealth Professor at the University of at Virginia Commonwealth University in the USA. And Professor Bandyapadhyay received his BTech in Electronics and Electrical and Communication Engineering from IIT Kharagpur a long time back. And then he did his master's from Southern Illinois University in USA and a PhD from Purdue University, working with Professor Supriyo Datta. Then he actually stayed there for a year and moved to University of Notre Dame and worked there for 9 years. And then he was taken to University of Nebraska Lincoln, the famous magnetism group of Professor David Salmeyer. And there he stayed till 2001. And then he moved to Virginia Commonwealth University as a Commonwealth professor. He received many awards and accolades. The list is endless, so I just mention a few. He was an IEEE nanotechnology distinguished lecturer, and he was also a IEEE Pioneer in Nanotechnology Award, winner of IEEE Pioneer Nanotechnology Award, and he was a Jefferson Fellow of U.S. National Academy of Science and a Sigma Psi professor, and he is a fellow of American Physical Society, IEEE, Electrochemical Society, Institute of Physics, London, as well as American Association for Advancement of Science. So with that, I would request Professor Bandyapadhyay to kindly deliver his talk.
Okay. Hello. This is on. This is on. Can you hear me? Okay. Very good. Okay. So when Professor Borman asked me to give this talk, I told him that I was not going to give a talk on my specialization. And that is because if you're not in my specialization, and I gave a talk on my specialization, you'd be bored to tears. You probably would not even come to the talk. I wouldn't if I were you. So I said I was going to give a talk that would be of general appeal. So this is the talk. And by the way, this is Friday afternoon, right? So you're looking forward to the weekend. I don't know what Indian students do over weekends. American students usually go to a bar and get drunk, but hopefully you don't do that. But nonetheless, Friday afternoon talk has to be a fun talk. And if it's not a fun talk, then what's the point? So let's begin the fun by showing a picture of this gentleman. Does anybody recognize him? Well, he's Nikolai Kardashev, and he's basically a Soviet astronomer, born sometime in the 1930s, and of course deceased now. He was an astrophysicist, but his claim to fame has nothing to do with astrophysics. In fact, it has something to do with something called the Kardashev scale, which some of you may have heard of. And the Kardashev scale is a scale that measures the degree of technological prowess, the technological advancement of a civilization. So the type 1 civilization is a civilization that can harness all the energy that reaches its home planet from its parent star, which in our case would be about 17 watts. So we're not a type 1 civilization yet. And it will take us probably about another century or so to become a type 1 civilization. And then there is a more advanced type 2 civilization that can harness all the energy radiated by its parent star, including that which does not reach its planet. So it's all the energy that is available in its solar system. If you can tap all that energy, then you're type 2 civilization. And then type 3 can harness all the energy or power available in its own galaxy, which in the case of the Milky Way is about 10 to the power 37 watts. And then there's a type 4 that can harness all the energy available in the universe. So that's the highest level, type 4. Now, there is also talk of a type 5 civilization, which was not in the original Kardashev scale, but it is a civilization that can harness not only all the energy available in the universe, but also in parallel universes. And because it can avail energy from our access parallel universes, and the laws of physics can be different in parallel universes, it is believed that a type 5 civilization would have the technical capability to alter the laws of physics. So there is probably no such thing as a type 5 civilization, and most likely there isn't a type 4 civilization in our universe either, but there may be type 1, type 2, type 3 civilizations. Now, the reason I brought this up is not to talk about the scale per se, but to point out that of all the things that one could have thought of in benchmarking the technological prowess of a civilization, it's energy that is used. It's not how much computer technology you have, it's not how many elements of the periodic table and beyond the periodic table that you can master. It's not what your chemistry knowledge is. None of that. It's how much energy you can command. So that's very interesting that technological prowess is measured in terms of how much energy you can access and use, and not anything else. And then there is this person who probably is a more familiar individual. Recognize him? Nobody. If you watch Discovery Channel, which is, I believe, available here, and there's a program called NOVA, and it's a science program, and this person used to lead that program. His name is Carl Sagan, and he's an astrophysicist from Cornell University, very famous person. And he had a different way of measuring the civilizational progress, civilizational power of the civilization. And he used the letter A assigned to a civilization that has 1 million bits of information, which is nothing, very little. And each successive letter represents an order of magnitude increase. So a level Z civilization will have 10 to the power 31 bits of information. And it turns out that in the year 2018, this you can actually measure. In the year 2018, we're at 0.73 J civilization. That's the human race. Now, what is interesting in this case is that one uses energy to measure our civilization progress, and the other uses information. And actually, the two are related. And so this whole talk is about the relationship between energy and information. And the reason that there is this, before we go there, you can see that because of these two measures of our civilization progress, the two most important infrastructures for any civilization, including us, are energy and information because they define our civilization's level of technical advancement. Okay? So I will talk about the link between energy and civilization a little later, but basically the link exists because information is knowledge, and knowledge is not free. It takes a lot of energy to acquire knowledge, to communicate, sense, process, and store information. Huge amount of energy is required to do that. And that is why energy and information are related. So today, 5 to 10% of the energy generated in the US is used by computers. This includes mainframes, this includes laptops, iPads, even cell phones, which are computing devices. And by 2030, it's projected that 25% of the energy generated in the US will be used up by the computers in the US. So with the present technology that we have, 300 Google searches will consume enough energy to boil 1 liter of water at room temperature. So when you do this Google searches, you're actually using up a lot of energy. So there's this intimate relationship between energy and information, and information processing devices like laptops, for example, consume a very significant fraction of the energy available to a nation. And not just this, but we as humans are also computers of some kind. and 20% of the calories that we consume is used by our brain to think. And so you can imagine how much of a persuasion it was for our ancestors in the savannas in East Europe, East Africa. Uh, they had to forage that much more for food in order to be able to think, because 20% of the food that they ate, the calories generated from the food, was used up by their brains to think and make them advance from this to what we have today. Does anybody recognize this tree? What kind of a tree this is? If you look at this picture, you will know immediately that this is East Africa, because this is called a baobab tree. It's very special. You can see a unique canopy, and it only grows there in East Africa. Okay, so in today, if you go to the state of Ohio in US, there are many big data centers. And if you pass by these data centers, you'll actually feel hot. I mean, I'm not making this up. You actually walk by this data center, you will feel a rise in temperature, because these data centers consume more energy than the city, some fairly large cities like the city of Athens in Greece, which has more than 1 million population. And the carbon footprint, the pollution that these data centers generate is huge. It's more than the pollution generated by a nation like Malaysia. And before the war between Ukraine and Russia, Ukraine was planning on building a cryptocurrency mining data center, and it required that the government build a nuclear power plant right next to the data center, because the energy requirement for this data center was projected to be about 2 to 3 gigawatts, just one data center. So huge amounts of energy is required for the information processing, storing, processing, communicating, and sensing information. Okay. So information processing by its very nature is extremely energy hungry. And this is one of the reasons why there is a link between energy and information in gauging or benchmarking our civilization's technical level of advancement. Now, this is a very interesting map that shows that there is a correlation between PC pervasiveness and energy store usage per capita. So you can see that, oops, go back. You can see that this is the map of energy consumption per capita. And here is India somewhere, not too high, but reasonably high. And here is the PC pervasiveness. Again, here is India. You can see that there's not a complete one-to-one correspondence, but there is a positive correlation between PC pervasiveness and energy consumption per capita. That means that a lot of this energy consumption is actually being consumed by the computers in the country. The countries with the highest number of PCs is this map, and you can see that energy consumption per capita correlates, not one-to-one, but correlates with PC pervasiveness. So this is another example of showing that the PCs or information processing devices consume a lot of energy. Otherwise, this would not happen. All right. So why is it that information takes so much energy? There's a very famous paper. This came out in Physics Today in 1991 by Rolf Landor, this gentleman. And this paper is based on a paper he wrote in 1961. And what he showed there was that something about irreversible computers. Do people know what is an irreversible computer versus a reversible computer? Anybody? Okay. So an irreversible computer is a computer where if you look at the output, by looking at the output, you cannot say what the input was. But if you could say what the input was, then it's a reversible computer. So reversible computers will allow you to determine what the input was from the output, but irreversible computers will not let you do that. If you look at just the output, you could not say what the input was. So irreversible computers have this property because during the computation, you actually have to throw away information. You cannot preserve all the information because you don't have enough resources to preserve all the information. So you throw away information, and when you do that, you constrict space, and that's why the computer becomes irreversible. And Landau's 1961 paper showed that there is a link between physical irreversibility and logical irreversibility. This is logical irreversibility. Logical means that computation, you cannot say what the input was and the output. But such a computer will also be physically irreversible, which means that it must dissipate energy. And what Landau showed is that the minimum energy that an irreversible computer must dissipate for bit of computation is kT times logarithm of 2. K is the Boltzmann constant, T is the absolute temperature. And at room temperature, this number is about 2.9 times 21 joules, which is about 7 times 10 to the minus 21 calories. And today's best technology will allow you to compute one bit of information by expending an energy of about 4 times 10 to the minus 19 joules. So we are roughly 2 orders of magnitude behind the Landau today. Best technology. And then, of course, there is this reversible computers, which in principle will not dissipate energy, but they require much more overhead than irreversible computers. If you factor in the energy cost of the overhead, for example, if you're doing quantum computers, which do not dissipate energy, quite frequently we will have to cool the quantum computers. They don't want to room temperature. So there's energy cost associated with cooling, cryogenics, etc. And if you add all of that up, actually you don't save energy. So there's always this very high overhead cost when you do reversible. Now, why would anybody care about these fundamental limits like KTL and 2? Why would I care if this is the minimum energy that I cannot cross this, I cannot do anything with this? Why would I care about it? So why bother, right? So why bother is, let's say that you are walking from block, whatever this is, sector 3, right? Sector 3 to sector 5 of Salt Lake, and you come across this individual here. Now, don't try to wrestle with it, because his technology may be a billion years ahead of yours, and you will not win the wrestling match, guaranteed. So don't accost him, but you will know that no matter how much better he is compared to you or she is, this individual's technology can be much better than yours, but even this character cannot beat the Landau limit. So you know the extent of the power such an alien can have, but you can't. Even they cannot beat the Landau limit. So that's the utility of this fundamental limits, right? So I'll give you a very simple proof. I decided at the beginning not to make this talk technical. So most of the talk will not have any math, but this is one little bit of math that I have here. So from the laws of thermodynamics, the energy change in any process is K times T delta S. S is the entropy. This is the Shannon entropy. So this is the energy change. Okay, and because of the second law of thermodynamics, this delta T, the change in the temperature, cannot be negative. So its minimum value is 0. So the minimum change in energy is kT times delta S. So delta S is the change in entropy. So what is this entropy, right? So the entropy is this following thing, that let's say that there's a system which can exist in n different states. And P sub I is the probability that it is in the ith state. So P sub I times the logarithm of P sub I summed over all the states, that's the Shannon entropy. Now, if you have a binary device, which is the simplest computing device, it's a switch that switches between two binary bits, 0 and 1. If you have such a device, then the number of allowed states, of course, is 2, just 2 states, binary bit 0 and binary bit 1. So this summation has only 2 terms. And now let's say that you have an irreversible computer, you did an operation and you found what is the output state. But you cannot predict the input state from the output state because it is irreversible. So you have to say that there was 50% probability that the input initial state was bit 1 and 50% probability it was bit 0. So initially you have this, that the probability of being in bit 0 is the same as the probability of being in bit 1, and each is 50%. So if you calculate the initial entropy, it's 0.5 times logarithm of 0.5, this, which is minus logarithm of 2. Right? Now, after you have done your logic operation, you can go and measure the output. So you know the output bit with absolute certainty. So it's either 0 or 1. So in the first case, the probability, okay, say it's 1. So the probability of being in 0 is 0, and the probability of being in 1 is exactly 100%, 1. Or the probability of being in 0 is 1, and the probability of being in 1 is 0. So in both cases, you can see that the final entropy is 0, because if you put pi equal to 1, logarithm of 1 is 0, so this becomes 0, plus pi 0, if pi is 0, then this term is also 0. Actually, this is the logarithm of 0, which is minus infinity, but if you do L'Hopital's rule, you'll find that when p is 0, this quantity is 0. So it's 0 plus 0 is equal to 0. That's the final state. So if you change in entropy, is S final minus S initial, is 0 minus this, which is logarithm of 2, and then if you take this and substitute it here, you get this result. This is the
why you are taking the probability to be 0 or 1 in the final.
Because it's a binary device. It can only have a 0 state or a 1 state. It cannot have any other state.
Yeah, but probability can take between 0 to 1.
True. But what I'm saying is that after I complete my operation, I can go and measure whether it is 0 or 1. And once I measure it is 0, it's 100% probability of being in 0, 0% probability of being in 1. Because I've collapsed the probability. Right? So the final, you can understand the final, right? That after the operation is complete, I go and measure. There is no more probability. It's all completely deterministic. So that's why either the probability of 0 is 0 and probability of 1 is 1, or other way around. Probability of 1 is 0 and the probability of 0 is 1. So these are only two probabilities, and in both cases, there is final is 0. So that's how you could do that. Now, initially, I don't know. It's 50-50, right? So that's why initially, the initial probability is minus logarithm of 2. So this is the simple proof. Actually, this was not Landauer's proof. You go read Landauer's 1961 paper. That proof is much more complicated. It's the 3 or 4 page paper, right? And this is half a page. This proof was shown to me by one of my friends, Bhavani Rajchodri, who is a professor at University of California at Los Angeles, and he came up with this extremely elegant proof.
What this proof is saying?
So what this proof is saying is that if you have a binary device, which is the simplest device, simplest computing device, the minimum energy that you will dissipate to switch the device is kT times logarithm. So you cannot, any other computing device will be more complicated and therefore dissipate more energy than kT will do. This is the absolute minimum.
This is the minimum energy.
Yes. Yes. So this is the minimum delta E. You cannot dissipate any less than this. Okay. So now where is this energy dissipation coming from? It mostly, in the case of our computers, it mostly comes from the hardware. The hardware is where the energy is dissipated. So conventional computing circuits, as you know, are made up of transistors. You can see that 99.999% of the computers that are around today use transistors. There are other non-transistor devices, but they're minor. By far, the mainstream devices. So I'll show you a picture of the original transistor. This is preserved in a museum in New Jersey. This is the first transistor made by Gordon, Breton, and Shockley in the late 1940s, and they got the Nobel Prize. So it's not preserved in a jar in a museum. When I was an undergraduate student in the late 1970s, transistors looked like this. I remember ordering these kinds of transistors onto breadboards and things like that. This is what the transistors looked like in the late 1970s. Today, the transistor looks like this. Actually, today it doesn't even look like this. In that year, early 2000, it looked like this with the mushroom gate. This is a MOSFET transistor. It's a gate contact, and you can see that this is 50 nanometer size. And the reason I show this is in the year 2003, for the first time, the transistor became smaller than a virus. So this is a influenza virus. Size is about 100 nanometers. Oops. Yeah. Right. So these days, actually, we have different types of transistors called FinFETs, which don't quite look like this. It has pins and other kinds of things. And they're smaller. They're smaller than 50 nanometers. They're in the 10 nanometer size. but I will not go there. So let me just talk about something about transistors that you may or may not know. So the most numerous species, living beings on this planet today, are not humans, but ants. I mean, there are only 8 billion humans, but there is more than 1 trillion ants. More than 1 trillion ants on the planet. But transistors outnumber ants. The number of transistors on the planet is larger than the number of ants. And that happened around the year 2000. Now, most people will tell you that the most important invention in the history of mankind is the wheel. And it is. But the number 2 important invention in the history of mankind is transistors. If you look at the use, in terms of the use matrix, transistors are only second to the wheel, and nothing else. So the issue is that I said that most of the energy dissipation or energy cost of computation comes from the hardware, which means they come from the transistor. And there is an enormous energy cost associated with using a transistor, switching a transistor to do computation. All digital computation is basically switching on and off a transistor switch. Whether it's digital signal processing, digital computation, all you're doing is switching on and off a transistor switch. And you dissipate an enormous amount of energy. If you go and ask chip manufacturers how much energy a transistor dissipates in that chip, they will never tell you that. That's a secret. But you can figure this out if you're smart enough. So this is something that you can find out from Intel's data sheet. This is a fairly old transistor. 2015 is when this was released. And it employs 14 nanometer FinFET technology. And if you look at the data sheet, it will tell you it dissipates 91 watts of power at 4 gigahertz clock frequency. And it has 1.75 billion transistors. And roughly 10% of those 1.75 billion transistors are switching at any given time. So from this data, you can actually calculate what is the energy dissipated per transistor. If you neglect all other energy dissipated in the wires and things like that, which are negligible compared to the energy dissipated in the transistor, then you can do this calculation. So the energy dissipated per transistor is the power in the chip, which is 91 watts, divided by the number of transistors, which is 1.75 billion, divided by the fraction of them that is switching on and off at any given time, which is 10%, 0.1, and then the clock frequency, 4 gigahertz. And it turns out that the energy is 130 attojoules. So attojoule is 10 to the minus negative 18. That is what an energy, a transistor in this chip would dissipate on the average. Now, you have heard of Moore's law, perhaps, which says that in order for the electronics industry to remain commercially viable, the number of chips on a number of transistors on a chip should roughly double every 18 months. That's Moore's law. Gordon Moore was the founder of Intel. So if you go by that Moore's law, this was 2015, then in 2020, you should have had the 5 nanometer node. And with that technology, the transistor count in the chip, 20 billion. And the clock frequency was already 4 gigahertz. It was targeted at 10 gigahertz in 2020. We didn't get there. And there is a good reason why we did not get there. But this was the projection. Right? Now assume that the transistor still dissipates that 130 attojoules of energy. So let's calculate how much energy will be dissipated in a chip which has a 5 nanometer size transistor, 20 billion transistors, clock frequency of 10 gigahertz. So you go into that calculation, right? So you have each transistor dissipating 130 attojoules of energy. Clock frequency is 10 gigahertz, 10 to the power 10. Transistor count goes up to 2 times 10 to the power 10, and the activity level is still 10%. You can see that the power that will be dissipated in the chip, 2.6 kilowatts.
One clock cycle.
This is the energy dissipated. Yeah. So not the energy. This is the power. Sorry.
No, I mean the first expression.
Yeah.
It's in one clock cycle.
In one
But
clock
of
cycle.
course, computation will take many clock cycles.
Right. Exactly. This is in one switching event. In one switching event, one clock cycle, as you say, 120 hours. So this will be the power, and there is no technology known to mankind that can remove this kind of power from a chip. There's no heat sinking technology that we know of. In fact, this kind of power, this is a chip size about a centimeter. So the power density is 2.6 kilowatts per square centimeter. And that is actually more than the power dissipated in the rocket nozzle. So this is the reason why he never got here. Because we could not figure out how to remove this kind of heat from the chip, and the chip would melt immediately. So what to do about this? Well, we certainly cannot, we don't want to decrease clock frequency and make it slower. Don't want to decrease the transistor count and make the chip less powerful. And we don't want to decrease activity level because then we're not really utilizing the circuit efficiently. So we cannot decrease any of this. The only thing we must decrease is this one. This one.
Reducing clock is one of the strategies to do.
So then you're going to make your computer slower.
But it can be multitasking.
No matter what, you don't want to reduce the
That I
chips.
transition count cannot be.
No, not transistor count, even the clock frequency. You don't want to reduce it because you don't want to give up speed. You want to increase speed, no matter what. I mean, you can go to better architectures and more parallelization, etc. But you never want to reduce clock frequency. So the only thing that you can and will and should reduce is this energy dissipated per switching event. So how do you do that? Okay, we'll talk about that in a minute. But before we go there, let's try to understand where does this energy dissipation in a transistor come from? So some of you know something about transistors, but maybe not all of you know. But before I go there, I just want to say that in order to reduce that energy dissipation, in order to reduce this number here, what I would like to do is there are three possible approaches to reducing this. So these three possible approaches are I can use a different device, not a transistor, something else, and use the same architecture. Or I can use the same device, transistor, but use a different architecture. Or if I am most radical, I will use a different device and a different architecture to reduce the energy cost of computation. So how do I do this? Before I go there, let me talk about where does this energy dissipation in the transistor come from. Right? So where does the energy dissipation come from? So you can think of the transistor essentially as a switch. It has two states, on and off, and one of them encodes binary bit 0 and the other one encodes binary bit 1. And so every time you do any digital signal processing or computation, you're flicking the switch from up to down, from on to off to off. So that's all you're doing. Right? The transistor acts like a switch, binary digital bit 0 and 1 are encoded in the on and off states, and every time you switch, you just switch the switch. So in the on state of the transistor is the conducting state of the transistor. So you have lots of charges in the transistor's channel. The off state is the non-conducting state or insulating state. And so you have very little charges in the channel. So when you switch the transistor, you're going from a state that has lots of charges in the channel of the transistor to a state which has very few charges. So you're changing the amount of charges in the channel. This is true of any charge-based device because charge is a scalar quantity. It only has magnitude, it's not a vector, it doesn't have a direction. So if you want to encode information, digital bit information in charge, you can only do it in the magnitude. So you can only do it in the following way, that more charges is one bit of information, less charges is the other bit. More charges is bit 1 and less charges is bit 0 or vice versa. So every time you switch, you have to change the amount of charges in the channel. And when you change the amount of charges in the channel, you invariably create a current. And that current dissipates energy. So you can look at this. This is a very simple math. So every time the transistor switches, you must change the charge from Q1 to Q2 or vice versa in some time delta t, resulting in a current which is this quantity here, delta Q over delta t, where delta Q is the change in the charge. Now, the energy dissipation is the power times the time. Power is I squared R times delta t. So you can work through this and you get this delta Q times I times R. Now let me define a quantity delta V, which is I times R. I is this current I. Here. R is the resistance in the path of this current. And so this is the energy that you will dissipate in switching a transistor because it is a charge-based device. All right. Now I want to point out to you that this delta V is not independent of the switching time. This delta V is this. And so for a fixed delta Q and R, this quantity delta V is inversely proportional to delta Q. And so what does that tell you? It tells you that if you switch faster, you will need a bigger delta V and therefore you will dissipate more energy. That's number one. Number two is you want your two logic levels to be well separated so that you can always distinguish between them. All right? Otherwise, if there is noise, then you will lose the distinguishability. So you need a larger delta Q for higher reliability. So if you need higher reliability, you will need a larger delta Q, and therefore you will also dissipate more energy. So the moral of the story is there is no free lunch. If you want something, you have to pay for it. If you want more reliability, you dissipate more energy. If you want more speed, you will dissipate more energy. Okay? So if you flip the switch faster, you will spend more energy. Now you all know about 5G, 6G.
This earlier slide,
Yes.
this heating is mainly due to this joule heating.
Yeah. Joule heating. Correct.
So in principle, means logically, let's say we come up with someday this superconductor.
Yeah, superconductor is one possibility, yes.
Then joule heating will be gone.
Joule heating will be gone. There are other possibilities also that I will show you.
But I'm saying it's still the fundamental limit, what you have earlier said.
This is for charge-based devices that has an R.
No, but I'm saying it's fundamental cost, the lander cost.
Yes. That has nothing to do with device. It's the same. It depends on thermodynamics. It doesn't matter whether you use superconductor.
Earlier value,
Yes.
that contribution is coming both from joule heating as well as from lander.
So here I just showed you what is the energy dissipated. This is the bulk. 90% of the energy dissipated in a transistor, more than 90% is this one here. Landau limit is different. Landau limit has to do, it doesn't matter whether you use transistors or some other thing. You cannot cross the KT.
So I'm saying the earlier slide, this came to
Oh.
minus 18, what you have calculated.
Let me go back. Yeah.
This kilowatt.
Uh-huh.
Here both these joule heating component as well as lander component.
No, so this is actually, yes, probably all, not land, these are not two different components. Landau component is a limit. This is the cost for energy dissipation in transistor is mostly joule heating. And this number is the transistor of today. So I calculated this number from Intel's data sheet. So transistor of today dissipates this amount of energy. Where does it come from? Mostly from what I just showed you.
These joule heating.
Yes, mostly from this one. So, you hear about this 5G and 6G technology, and 5G now, 6G is not far away, and you know that the frequencies are 4G is 0.7 to 2.5 gigahertz, 5G is 20 gigahertz and up, and 6G is 110 gigahertz. So these are high, extremely high frequencies, and that means that you're switching faster. So if you're switching faster, based on what I just said, you need more energy. So as you go to this 5G, 6G, 7G, etc., your energy demand goes up exponentially, and that's an issue. And so carriers are now looking at this issue, and they're now very mindful of it because they realize when they went from 4G to 5G that their energy consumption went up by a factor of 2 immediately. And so operators are facing a power cost crunch, and that is why the cost of this 5G network will be a lot more than 4G and 6G, even more, mostly because of the energy demand, that you need more energy to go from 5G to 6G to 7G, etc. Okay, so now I said that there are 3 possible approaches. You can change the device. Don't use a transistor, use something else. That might reduce your energy cost. Or you can change the architecture, or you can change both. So let's talk about the first first case where you're changing the device and you're trying to find a more energy efficient alternative to the transistor. So one such thing is a magnet. Okay, this is related to my area of research. So if you take a ferromagnet and you shape it like an elliptical disc like this, then the magnetization can have only two possible orientations in the stable state, steady state, stable orientation. Along the major axis of the ellipse, either pointing to the right or pointing to the left. Those are the two allowed magnetization orientations. And so you can use one to encode the binary bit 1, or right pointing 1, and the left pointing 1 to encode the binary bit 0. So this is not a transistor, and you can actually switch from 1 to 0. All you have to do is flip the magnetization. And you can do that without passing any current through the magnet. There are many ways of doing this. None of them requires passing a current through the magnet. So that Joule heating business, that I square R, is 0 in this case. Because you're not passing any current, there's no I, so there's no I square R. Right? So how do you do this? There are many ways of doing this. The one that my group works in is called straintronics. So what you do there is you place this magnet on a piezoelectric substrate, and the piezoelectric is pulled in a certain direction, and then you put two electrodes, and you apply a voltage between these two shorted electrodes and the back contact, which is a conducting substrate grounded. And when you do that, if the electric field from this gate voltage is anti-parallel to the direction of pulling, then you will create compressive stress along the line joining these two electrodes and tensile stress in the perpendicular direction. And if you change the voltage polarity, it will be the opposite. So you have tensile stress along the line joining the two electrodes and compressive perpendicular. So now tensile stress is positive, compressive stress is negative. And this material has magnetostriction. Okay, so it's not iron, it's something like maybe cobalt or nickel, etc., which is a magnetostrictive material. And magnetostriction also has a sign, positive or negative magnetostriction. And the product of the stress and the magnetostriction has a negative sign. Then if we apply the stress, the magnetization will rotate away from the easy axis or the major axis towards the minor axis. And if you release the stress as soon as this 90-degree rotation has been completed, there is an inertial torque acting on the magnetization because the magnetization lifts out of the plane when it rotates. And that inertial torque will make it rotate by another 90 degree and flip it, make it rotate by 180 degree. And this is how you can flip. And you can see that in this case, no current passed through the magnet at all. So there's no I square R. Now this is actually very energy efficient, and we have lots of theoretical and experimental results on this. And according to theory, only about 1 attojoule, which is 120 times the Landau limit, would be dissipated to switch in 1 nanosecond. Remember that if you switch faster, you will dissipate more energy. So if you switch in 1 nanosecond, you will expend about 1 attojoule of energy. So yes, there is, and so that we call that Landau damping. Sorry, Gilbert damping in this case. And so all of that is taken into account.
Even with that, it's better.
Yeah. So this is the histories. There's no eddy current loss, by the way, because this is a nanomagnet. The energy required to form an eddy current loop would be tremendous. It doesn't form. But there is this Gilbert damping business, frictional loss, what you call hysteresis. That is taken into account. And there's also a CV squared loss, which is in the electric circuit, and all of that together is about 1 atom. So because of this is so energy efficient, it was actually featured in Nature. And there's a book now by yours truly. And so we discussed a lot of this straintronic switching business in that one. All right. So I just want to make a comparison here. You can switch a magnet in many ways. There is something called a spin transfer torque, which requires passing a spin polarized current to a magnet. That will take about 10 to 100 femtojoules. Spin orbit torque, similar to spin transfer torque, but it uses an additional feature called giant spin Hall effect. It's about 10 times more energy efficient. Transistor is this one, 100 attojoules. Memristor is another device I will not talk about. It's about same as transistor. Domain wall devices are another type of magnetic devices, and you can switch a magnetic device by moving domain wall. Takes about 40 attributes, and strain toric hour takes between 1 to 10 attributes. The other thing that I want to point out is magnetic devices are non-volatile. So if you put the magnetic device in a state, say 0 state or 1 state, and go away and come back 1 year later, it's still in that state. But that will not be true of transistors because it's a charge-based device, charges leak out, and so it's not volatile.
There is now also this magnon current induced switching, which is eventually going to beat the spintronic limit.
Maybe, yeah.
Because here only the Gilbert damping is the only, dissipating torque.
Mm-hmm.
And even spin orbit torque, or here you have some current.
Correct, yes.
So there is complete current free. Few works have come up. Probably you will have to add one.
Yeah, I don't know.
In this table.
Yeah, there may be more rows. I mean, we'll add more and more rows as more and more technology comes. So the second approach. The second approach is not changing the device, but using a different architecture. So how can I do this? So here's a picture. And many of you have probably seen this picture. This is Garry Kasparov playing chess with IBM's Deep Blue computer. And in this match, Kasparov lost, barely lost, but his brain was dissipating, human brain dissipates about 20 watts when it thinks, and IBM's Deep Blue dissipated several kilowatts. So energy for energy, the human brain is far more energy efficient than the world's best supercomputers. That's because the human brain does not work like a digital computer. It's a very different way of working. The interaction between the hippocampus and the neocortex is very difficult to replicate in electronic circuitry of any kind, magnetic or electronic or charge or something. So there are now these ideas about different architecture, neuromorphic, which is brain-inspired, but not quite like the brain. They can be more energy efficient than normal Boolean von Neumann type architectures that are used in today's computers. Then there is probabilistic computing, and have you all heard of p-bits? No one. Have you heard of qubits? You've heard of qubits, right? So a qubit is a quantum bit. The difference between a classical bit and a p-bit is a classical bit is either 0 or 1 all the time. A p-bit is sometimes 0 and sometimes 1 with certain probabilities of being 0 and certain probabilities of being 1. And a qubit is both 0 and 1 all the time because it's a coherent superposition of 0 and 1. So a p-bit is in between a bit and a qubit, something in between a bit. And there are now lots of work on using p-bits, probabilistic computing, to solve challenging problems, NP-hard problems, combinatorial optimization problems, mean cut, max cut problems. They have all been solved with p-bits. And you can implement p-bits also with magnets, but these magnets have almost circular shape so that the energy barrier in the magnets, the barrier that separates the one bit information from the other bit, the one orientation from the other, that is very small. So there's some randomness, and that randomness can actually be utilized to solve certain types of problems very efficiently. And then there's this belief networks, also called Bayesian inference engines. I work in this area. The belief networks are best when you're computing in the presence of uncertainty. For example, stock market behavior. You cannot predict it very easily. So Bayesian networks are very good for predicting stock market behavior or disease progression, how COVID progresses and so forth, things like that. And then its most common use is the following. Say you see an effect, and you know that that effect can arise from 5 different causes. Say I got pneumonia, and I don't know why I got pneumonia. I traveled to some country in Africa that has pneumonia. Maybe I got it from there. Or maybe yesterday I got soaked in the rain, and maybe that gave me pneumonia. Or maybe I ate something, and that had pneumonia bacteria in it, and I got pneumonia from that. So they're all possible causes. And what a belief network can do is very efficiently tell you which is the most likely cause based on the data. So this is another type of computer, and it's very useful in solving certain types of problems. And then, of course, there are quantum processes. So all these are non-traditional, non-conventional architectures, and they can be much more energy efficient than conventional architectures. There's also other advantages of this. Go back. Okay. So these neuromorphic architectures have another advantage, that they're more cyber secure. So they're more immune to hacking, for example. The typical cyber, say, your antivirus programs, how do they work, these antivirus programs? They look for specific patterns in the software. And if they see that pattern, they will kill that program, because that is probably a virus. But if there's a new virus which does not have that specific pattern, it cannot protect you. It does not recognize it as a virus. But there are neuromorphic architectures are now available. So this company here, Neuromorphic Cyber Microscope, designed by Louis Rose Lab with Sandia National Laboratory, the Department of Energy Laboratory, directly addresses all these limitations with its brain-inspired design. It can look for complex patterns that indicate specific bad apples. Bad apples are viruses, and all the while using less electricity than a standard 60-watt light bulb. So if you use this neuromorphic, neuro-inspired, you can go and read this neuro-inspired architecture. They're also more cyber secure. You have to do edge computing these days. Most of the viral attacks comes from when you have an edge device communicating with the server, the cloud. And most of the attacks are cloud-based. So you don't want to actually communicate with the cloud. You want to do all your information processing locally in the edge. And so you need two attributes. You don't have enough energy available. So you need to have very energy efficient devices for edge computing or Internet of Things. And at the same time, you cannot store the data somewhere else because you cannot go to the cloud. The cloud is dangerous. So you will need non-volatile devices. So for these things, magnetic architecture, edge computed magnetic architectures are extremely beneficial. So then the last thing I want to talk about is if you have different devices and different architectures. And so there are these magnetic devices that I talked about. That's a different device, different from transistors. They have these advantages of lower energy consumption and non-volatility. And then neuromorphic architectures, there are these things called spin neurons with MTJs, and I have papers on that, and domain wall synapses. So the neuromorphic computer usually has a neuron connected with synapses, rather than neuron. So you can make these synapses, emulate synapses with domain wall motion. Leaky integrated and fine neurons is a very useful type of neuron in the neural architecture. You can make that with magnetic devices, again, domain wall devices. And the reservoir computing, which is a type of computing that uses mostly memory, computing in memory. And then probabilistic computing can be done also with low barrier nanomagnets. So these are all very hot areas of research today, where you have different devices and different architectures. So, and then Bayesian inference engines, and we have made these with spintronic MTGs. Okay, so in summary, this is my last slide. In summary, the two most important infrastructures are energy and information, and they're linked. They're not independent of each other. So with this, I will stop, and if you have any questions and comments, you can email me. That's my email address. By the way, I gave this talk in the US National Academy of Science in 2020, and I gave this talk to the State Department, which is mostly politicians and bureaucrats, not scientists. And so you can actually, this talk is not exactly the same talk, but very similar. And that talk is on YouTube. So if you search under my name, you can find that in YouTube. It's posted on YouTube. So, I mean, I have no reservations about this talk. It's open to the public, nothing confidential. Okay, so that's all. And so thank you. And if you have any questions, I'm happy to answer.
So thank you, Professor Bandyapadhyay. It's very engrossing talk. So you can have some questions.
Okay, yes.
Yeah.
One small question. Last part of your presentation, your work is working with piezoelectric modeling.
Yes.
And you
pretty well competing with the idea. What about the size of the size of the device? They're about 100 nanometers right now, but we cannot go down to very small devices. There are devices called perpendicular magnetic anisotropic devices. We didn't talk about that's the detail. You can go down to about 20 nanometers. It's competitive, but probably not. I mean, now you can have transistors that are 5 nanometers in size. So we cannot go to 5 nanometers.
Can there be any magnetic phenomena at 5 nanometers?
Well, the 5 nanometers will be super paramagnetic problem, right? So,
No, but the perpendicular magnetic anisotropy would not be super power. They have huge anisotropy.
yes, huge anisotropic. So that one it can go to 20 nanometers. It can do production is in 20 nanometers. You may be able to go down below 20 nanometers.
So the patterning, nano patterning is the limitation instead of the phenomenon.
No, I mean, we can do nano patterning now. 5 nanometers we can do definitely.
Helium.
I mean, Ray has a machine that can do 5 nanometers. Cannot do 5 nanometers and maintain strong uniformity over the entire.
One Ratan has a question. Sir.
Just wondering that 5 nanometer
So this is quantum effects. The magnetism is based on a quantum effect. It's based on exchange interaction. So all of these quantum effects are there, and they will be included in. What you can do is you can. I mean, there is. I haven't done any modeling of nanomagnetism beyond the standard Landau-Lifshitz Hilbert model. I haven't really done anything that is exotically quantum mechanical. I mean, I've done some work on magnon coupling with photons and magnon coupling with photons, that kind of thing, but not really at that level. And I don't think that at this point that is, we're not there yet. When we get there, we probably will have to. Even the transistor, the people who do this transistor, they have some quantum effects included in them, but only heuristically. It's not fundamentally quantum. The fundamental transistor. We don't start from first principles. It's pretty close. I mean, we are mostly experimentalists. So we do mostly experiments, and our theories are not 100% matched with experiments, but are close enough. So I don't think that we are there yet. You're absolutely right that at some point this classical or semi-classical theories will not be working anymore. But at that point, I don't think that we will even have magnetism. Go to very small size, 1 nanometer is less, some nanometer, then you probably will not have ferromagnetism, super paramagnetism. We haven't worried about that yet.
Instead of transistor, you say this magnetic things. Still, the magnetic thing is just like working classically, 0, 1. That's all.
Yes, yes.
It is neither probabilistic nor nothing.
Very classical. We can do probabilistic thing with magnet, but I didn't talk about that. So that requires a magnet which has a circular shape. So circular shape means that the energy barrier separating the 1 state and the 0 state is 0. That's not
Theoretically, when any theoretical result is there, that probabilistic will give me more computing power than a
Oh yes,
deterministic
many
result.
groups. Many groups, including mine. So we can do with probabilistic computing, we solve certain classes of problems, like traveling salesman problem, or mean cut, max cut type of problems. Those types of combinatorial optimization problems you can solve extremely efficiently, far more efficiently with probabilistic. Then even things like Ising problems, they're also Boltzmann machines, Boltzmann engines. In fact, there's a very famous paper in Nature that came out of my old advisors group, factorization with probabilistic. Very efficient.
So do you use the transistors?
No magnets.
So,
The probabilistic
these
magnets.
probabilistic operations, are you optimizing trying to reduce the time complexity or the energy complexity?
No, probabilistic computing is you're trying to solve a problem,
Right.
with as fast as possible.
You said efficient. So what the definition of
So efficiently is in terms of time.
using time? Not energy.
No, not. In this case, it so happens that the energy is also small, but not necessarily. We don't try to minimize energy. No, we try to minimize time.
So what is the belief algorithm you use in
So the Bayesian, we use typical Bayesian algorithm. Bayesian algorithms are interesting because they need very unique thing. They need what we call combination nodes, what we call parent-child. So normally what happens is that the connections between different combination nodes is reciprocal. So going this way versus going this way is the same. Okay? But that will not work for Bayesian. The reason is that there's a parent node and the child node. And the child listens to the parent, but the parent doesn't listen to the child. That is of course not a human parent. That is, this is a computational parent. So that requires a non-reciprocal. That is, the parent always orders the child, but not the other way around. So that non-reciprocal thing actually you can real some papers on. You can implement this non-reciprocity. Very difficult to do. Cannot do in transistor level, but you can do with magnets. And that is the way you do this with magnets. You have two magnets. One is bigger and one is smaller. The bigger one has a bigger energy value. The smaller one has a smaller energy value. And you apply stress. Stress depresses the energy value. And you can make the energy value in the smaller one go to zero, but not in the bigger one because that is a much bigger energy value. So now, this person, this node can actually dictate curves to this node because there's no energy barrier. So the dipole interaction doesn't have to overcome any energy barrier. So this one follows that, but not the other one. So we have papers on that, theory papers. That is required. I actually worked with a person, Amit Trivedi. He was my student a long time ago, undergraduate student. He's now a professor at University of Illinois in Chicago. So he's an expert on Bayesian. I have lots of papers. So he's shown that with this magnets, the energy cost is about 1 order of magnitude smaller compared to resistors. And we have other papers that are associated memory and things like that. Neuromorphic network also. The energy cost with magnets is 2 or 3 orders of magnitude smaller. And if you implement those neural networks. So, I mean, the reason we went into this magnets is basically we don't have more energy. And on top of that is non-molecular.
So what's your thought on complete reduction of Joule? Because actually, Coulomb's law.
So if you the way you can remove Joule heating, the way we did in magnets, you don't have any I. Right? There's an I squared R off. I is 0, there's no current going through it. So there's no I squared R loss. That loss is not there. But there's, of course, that doesn't mean there's no loss. There's loss associated with Gilbert damping, what we call hysteresis. That sort of thing is there, but it's much smaller than Joule. So our loss is not 0, but
This
it's
is also saturating. I'm saying this Coulomb's law is saying that computational power, I mean, the computational cost is actually reducing every year, but it is also saturating.
no, but computational cost per computation is reducing, but the number of computations is going up much more rapidly than that. So the energy consumed by computers is increasing tremendously from year to year. In fact, total amount of energy available on this planet at any given time is about 10 to the power 27 joules. This is from renewables and non-renewables, from coal, gas, oil, solar, hydro, everything. About 10 to the power 27 joules at any given time. And if you look at the way computation is progressing, artificial intelligence, smart cities, smart factories, driverless cars, and things like that. This is exploding, growing by 100 times every 2 years. And so if that's the case, then calculation, and I don't have that reference with me right now, but there are calculations that show that by the year 2060, if you are growing at this rate, computers will consume 10 to the power 27 joules. That will eat up all the energy available on the planet and leave nothing for anything else.
That energy, is it limiting part or is it fundamental to the most?
Whatever, I mean, you can say that it is still 130 attributes. Take that number, 130 attributes to the 1 given number. And so you can see that through 10 to the power 27 joules, how many bits are there? That is the number of bits we'll be doing in the year 2060. So unless we can reduce from 130 joules to much less than one, probably even less than 1 attribute, 130 joules to less than 1 attribute, we will have a crunch. We will run out of energy.
So,
In memory computing, that possibly charge-based.
Yes, right now people do the job.
How they
So they use SRAMs, right? So static SRAMs, and so that is
phase change for PC.
also PC RAM. So PC RAMs, phase change RAM, resistors, and all of these are there. Resistor based is SRAMs. It's big. SRAMs are big.
So only advantage is that you are avoiding the switch.
Yeah, but SRAMs are not volatile. So you get the non-volatility. That's why.
That is also energy wise.
Yeah, energy wise, SRAMs are pretty energy expensive. You know.
Because they are operating away from the switching unit.
No, SRAMs is the way the SRAMs work is you flash memory. So the way flash memory works is you have trapped charges in the gate oxide and write charges, read charges, and you get current, high level of current, to write charges. So there's a lot of I square R laws there.
so we'll take a new question. So, request Professor Government.
Oh, thank you. Oh, great. Thank you so much.
Thank you, Professor.
All right.